Alright, so this is on your definition of derivative notes. Now we've went over this with the whole function thing in the beginning of the lesson, but let's go ahead and review. So our definition of derivative, as you see, is right here. So this is what we went over. I'm going to go ahead and quickly review that with you. So we said that if we have a function, remember how me and Deja were the functions? Okay, and if I want the derivative, so the slope between these 2 points, slope between those 2 points that we see, that's our secant line slope. But remember that we don't want secant line slope, we want tangent line slope because that's a derivative. Here's how we defined it. We said that was our x, and that means this was our f of x. And we said let's just assume that it's HOA. So let's say this distance from here to here is HOA, which makes this, since it's HOA to the right, x plus h, which means this dot right here, the height of that would be f of x plus h. So this, if this is my x1, that's really my y1, and that's my y2, and this is my x2. Good? So to get the slope of the secant line, we do y. Remember how us doing y2 minus y1 over x2 minus x1? We're still doing that. That's our AROC. We did that in the beginning of this unit. We said we do y2 minus y1 all over x2 minus x1, in which this really simplified to the top. You can't simplify any further. At the bottom, the x's will cancel out, and we'll have h left. So that was our average rate of change. Now let's take a look at the actual tangent line. Now you have a concept of tangent line and the slope of the tangent line. We know the tangent line is something that where it just veers up that one point and it cups the function. Remember that? Now, if the distance between these two were 0, remember how we had a little animation and we made this dot get closer and closer here? That makes a line that's tangent to the curve, which means my h needs to approach 0. So in order for us to have a derivative or a slope of a tangent line, we're looking at instantaneous rate of change, which is IROC. And we got that by doing, we want, remember the approaching concept is limit, we want the h to approach 0, and the rest of it basically stays the same. So we want it to be same, but we want the slope, because that's what the derivative does for you, find the slope at a certain point. However, this is a we want slope, but at that point, so we want the h to be closer and closer and closer to 0, and that's what we're talking about here. Now, this is our definition of derivative, just because that gives us the slope at that point. However, if we take a look at it, that's kind of like our L'Hopital's rule. So let's take I'm going to go ahead and apply L'Hopital's rule here for us. So my definition of derivative, once again, was limit as h approaches 0, because I want the distance to be 0, of my y2 minus y1 over x2 minus x1, which is just h. This is my definition of derivative. And let me go ahead and prove this to you by using L'Hopital's rule. Okay? So if I were to use L'Hopital's rule, which is this just means take the limit of it. If I were to plug in, you see how the h is approaching 0? That means all my h's are letters, and the rest of it is just numbers. I know it's really confusing because we usually view x as the variable and the rest of it as numbers, constants. But in this case, since h is approaching 0, the h's are going to be our actual variables, and the rest of it, the x's, are going to be our just numbers, okay? So if I were to plug this in, we'll get 0 over 0, but let's reconfirm that. So if we were to do this, we get f of x minus f of x over 0, which is 0 over 0, which causes us to use L'Hopital's rule, because we have 0 over 0 on my limit. So I'm going to apply L'Hopital's rule on my, let me see here, my h still approaches 0. L'Hopital's rule said for us to take the derivative of the top. That's what I'll do. Let's do one thing at a time. So that gives us f prime, because we're in Canton wrapper, and leave the inside alone. So I'm going to leave the inside as x plus h. So that's the derivative of the wrapper times the derivative of the candy. Remember, I'm taking the derivative of the letter, so the derivative of x, which is just a number, is equal to 0, and that's times 1, minus this f of x, okay? Now, I know it says x in there. Remember, x was just a number, so if you imagine all the x's as numbers. That's really just a number itself, because it's y of number, so that just becomes 0. And derivative of h, which is a letter, is equal 1. And this really just becomes limit as h approaches 0 of f prime of x plus h, as you can see, over 1. Now we're going to evaluate the limit by plugging in 0, so this becomes f prime of x. So here's what we just ended up with. We said this is equivalent to f prime of x by using the L'Hopital's rule. So if you want to work on the definition of derivative, you can apply the L'Hopital's rule because it is limit, right? Derivative is within the definition of derivative, there's a limit in it. So you can apply the L'Hopital's rule and get to the point where it says a derivative.